Welcome back to the Deep Dive. Today, we're doing a really deep dig, literally into India's national policy on geothermal energy. It was notified in 2025, and the aim is, well, to unlock all that heat beneath our feet. Big goal, helping meet India's net zero targets for 2070.
Yeah, it's a fascinating area.
So our mission today, let's quickly unpack the science behind it, look at the policies, economic drivers, and maybe figure out why this huge power source often gets overlooked.
Okay, let's kick off with the scale because it's pretty mind-blowing. Geothermal energy is essentially just the Earth's own heat. It comes from deep inside, mostly from the slow decay of radioactive elements. Think things like uranium, potassium, deep in the mantle.
Right, natural heat.
Exactly. And here's the really wild part. Just the heat in the top 10,000 meters or so, it holds something like 50,000 times more energy than all the planet's oil and natural gas combined.
50,000 times. Wow, that's not a typo, you said.
Not a typo. It's an absolutely enormous resource.
A hidden powerhouse, truly. I mean, we see glimpses, right? Geysers, hot springs.
Yeah, those are the obvious signs.
But that's just the surface. The sources mention different types, like geopressurized, hot rock systems, and hydrothermal ones. And only hydrothermal is really used commercially now.
That's right. Hydrothermal is where you've got hot water or steam already naturally accessible, easier to tap into.
Make sense?
Hot rock is, well, trickier. You've got the heat, but you need to drill down and then pump water in to create steam. More complex, more expensive. So yeah, mostly we chase the spots where nature's done the plumbing work already.
Okay, so how does India's 2025 policy actually plan to tackle this? It sounds like it covers both the really hot stuff and the less hot resources, high and low enthalpy.
Exactly. It's comprehensive. High enthalpy means really hot temperatures, good for spinning turbines, generating electricity in the traditional way.
Okay.
Low to medium enthalpy is, well, cooler. Still very useful, though. Perfect for things like district heating, warming buildings, industrial processes, even for, like, geothermal cooling systems.
Right, direct use. Got it. Now let's talk policy levers. Money.
Yes.
'Cause that's always key, isn't it? The sources highlight major financial backing. 100% foreign direct investment is allowed.
Yes, 100% FDI is permitted, which is a big signal. And it's backed up with some serious fiscal incentives.
That's just
Well, you've got tax holidays, exemptions on import duties for equipment, concessional loans, cheaper borrowing, and something really important called viability gap funding, or VGF.
VGF, right. How does that work?
So the government basically chips in funds to make those early, maybe riskier projects financially viable until they can, stand on their own feet. It bridges the gap. And this support can run for up to 30 years for a project.
That's substantial. And here's something I found really interesting. The policy actively pushes for joint ventures with oil and gas companies, mineral companies.
Yes.
And it specifically promotes using old, abandoned oil and gas wells for geothermal. That seems smart.
It's very smart reuse. Think about it. The biggest hurdle often is that huge initial cost and risk of drilling exploration wells from scratch.
Right. Drilling's expensive.
Very. So by using existing wells, you potentially sidestep a lot of that initial cost. You already have a hole in the ground, often quite deep, and you have companies with the drilling expertise right there.
So you're leveraging existing infrastructure and skills, turning old fossil fuel sites into green energy hubs potential.
Precisely. Brownfield to greenfield, effectively. It also taps into that skilled workforce.
Okay, let's connect this back to the why. What are the big advantages? We know it's renewable.
It's renewable, yes. But the real kicker, I think, is its reliability. Unlike solar or wind, which depend on the weather or time of day, geothermal is just there, 204/7.
Baseload power. Always on.
Exactly. That kind of constant, reliable power is incredibly valuable for stabilizing the grid. Plus, once a plant is up and running, the operating costs are generally low and the carbon footprint is much smaller than fossil fuels.
But there's always a but, isn't there? The downsides. We mentioned the high initial costs already. What else? Location seems key.
Definitely location specific. You need the right geology. Areas with volcanic or tectonic activity are usually the prime spots, where the heat is closer to the surface or easier to access. You can't just drill anywhere.
In environmental concerns, drilling deep does carry risks, right?
It does. There's potential for land subsidence if you withdraw a lot of fluid, or even induced seismicity, small tremors caused by changing pressures deep underground. These need careful site assessment and ongoing management. Mitigation is key.
So it's a balancing act. Huge potential for reliable, clean energy, immense scale.
Uh-huh.
But you need careful planning, strategic investment, and ways to manage those site-specific risks.
That sums it up pretty well. It's not a magic bullet, but it's a powerful tool in the energy transition toolbox.
Which brings us to a final thought, especially thinking about that strategy of repurposing old wells and involving oil and gas companies.
Mm.
Considering the deep drilling know-how these companies have, but also the, let's say, different geological and heat flow challenges of geothermal compared to oil, how effectively can they really pivot? Can that existing expertise translate smoothly to unlock this, well, hidden giant beneath our feet?
That's the big question, isn't it?
It is. Something for you to think about until our next deep dive.